Hello, I am in Houten in the Netherlands, right in front of the main entrance of the brand new SKF R&D center. SKF is world #1 manufacturer of bearings, providing the reliable performance for anything which rotates in our real world. As a reliable rotating equipment performance provider, SKF is present in more than 150 countries around the globe. Now, the heart of the R&D of SKF lies here in these new buildings, opened in 2019, where the labs have been designed as one lab by their own users. So we have been invited to see how they use this facility to solve our real-life customer challenges and continuously win over friction and wear. Let's have a look. I wish this is how the bearings installed on top of my wind turbine nozzle or down deep in my mine were looking like. Let's talk to the expert to see what they have to say.
Good afternoon, everybody, or good morning, depending on where you're sitting on this planet. Welcome to this tour of the SKF R&D facilities. My name is Arnaud Ruelan, and together with my colleague Satwik Chatra, we will be guiding you through our R&D labs during the next hour. So we really hope you're full of energy, full of curiosity, because you're going to be walking a lot in this building during the next hour. So let's start by putting on some PPEs, safety glasses, a lab coat, some safety shoes for some of the testing area, and we can get going. Of course, you see those face masks. Considering the sanitary worldwide situation, you will understand that we will all be wearing those masks today, and we will do our best to limit the disturbance. So let's get going. You probably saw the chrome-plated bearing downstairs in our lobby. And you probably all know that a bearing actually looks more like this. Actually, this one has been sectioned so you can enjoy seeing the different components that consist the bearing, the rolling elements, the rings, the cage, etc. But actually, in many cases, you do not get to see the bearing because the bearing is encapsulated in some housing like this one with many connections to it. Sensors, lubrication systems, for example, this grease dispenser on this housing here. So let us show you how we fight against friction and wear on a daily basis. SKF has many laboratories across the world to provide direct support to our customers and to our own SKF application engineers. In this building, this is somewhat different. This is where the heart of R&D lies. This is where we develop solutions for today and tomorrow for application-driven innovation. So Satwik, you have been with SKF R&D for a bit longer than I have. Can you tell us what it is to work in this environment?
Yes, thank you very much, Arno. Definitely, I can share some insights about this organization. Everything we do in this organization is mainly to challenge the current technological status quo to come out with a better technology for our future. We believe in the way of doing our research that has a high impact on our partners globally. That includes our suppliers, our technical collaborators, and most importantly, our customers. When we say technical collaborators, they are our university partners. To name a few, like University Technical Centre at Imperial College of London, Insolio, and also at University of Twente in Netherlands. The technology and solutions developed in this R&D center here will be utilized by our partners globally, mainly to enable the predictability and solutions for the rotating equipment performances. If you look into the history of this organization, SKF R&D Center as an organization in Netherlands was started around 1970s. That means we have an experience of around 5 decades in serving our partners globally. When we started this organization, we started with the focus of application-driven R&D. Indeed, even today, we hold that focus, but along with that focus, we also added additional ones like developing technology and solutions to enable the reliable rotation. As an organization, we are organized based on competences and projects. Currently, we have competences in the areas of materials, tribology, lubrication systems, and prognostic and diagnostics. We utilize these competences to develop the technology and solution for many application sectors. To name a few, like railway, electric vehicles, metals, machine tools, circular economy, and many more. So today, to showcase everything in an hour, it will be very difficult. So we'll be focusing more on how we utilize these facilities to develop technology and solution for our customer problems. That means we will be focusing more on application-driven R&D. Definitely, when we elaborate our processes, we will be giving certain examples as applications. But bear in mind that those facilities are not meant only for those applications. It is just given as example. For further on this, my colleague Arno will speak how we are going to proceed in this lab tour. Thank you.
Well, actually, all I can say is let's get going. As you all know, R&D is an iterative process where we go back and forth between the different competence areas, different labs, and where we loop between testing and analysis and testing, etc. For practical reasons, it's obvious that this tour will be quite linear. We will start from our tribology room and end with a Q&A session where experts will wait and take your questions at the end of this tour in our experience center right here. But we're going to start with a tribology section. This is where we translate full bearing size challenges and contacts into single contact experiments to better understand and mimic what is going on in application. Christine is one of our senior tribologists, and I will let her explain what we do within our tribological facilities. Christine, please.
Thank you, Arno. So welcome everyone to the tribology facility, where we investigate the different tribological aspects that can occur in a bearing through single contact experiments. So to have a clear picture of what we do in this facility, let's take as an example, for example, the metal industry. In this industry, we have a lot of contaminants, like for example water, like for example particles and others that are present in the bearing environment. These contaminants can enter the bearings and influence the bearing lubrication. So this can lead to generate some kind of damages on our bearings and may lead to the early failures. In this facility, what we have is that we have different rigs, or what we call tribometers, that are used to study the influence of this contaminant, for example, on lubrication film thickness, on friction, on wear, on surface distress, and also on different kinds of phenomena that can occur in a bearing. So we using single contact experiments. So what we do is that we use these rigs to first study, to verify if these contaminants are responsible or are the root cause of the phenomena which is that we see in the field. And if this is the case, we propose solutions as a prevention, and we verify this solution using the same test rigs. So the proposed solution could be coatings, could be, for example, new materials like ceramics, could be also new surface treatment, or others depending on the nature of the contaminants. So first, what we're going to see is that we are going to study the influence of contamination on lubrication using a test trick, which is called the WAM test trick. And this trick will be introduced to you by my colleague, Ralph. To you, Ralph.
Thank you, Christine. Hello, everyone. This is the WAM ball and disc machine. It's a very versatile machine, and it can be used for many different types of experiments. But at the moment, it's set up for film thickness. And then here we can see that film thickness, we use the concept of interferometry. The glass disc is coated with a semi-reflective layer. Light is coming from the microscope and partly reflects on this layer and partly it reflects on the ball surface. And the difference in distance is then measured using color recognition. The accuracy of this method is about 10 nanometers. Currently, we are testing an oil. The ball is then positioned underneath the disc. That is lubricated with a few droplets of oil, and that is sufficient to build a film. When we then look at the image from the microscope, you can see that the oil is contaminated with drops of water, and the droplets are coming towards contact, but in fact they do not go through the contact, but they move around the contact, and then they gather in the outlet region. So the water in the oil does not have an effect on the actual film thickness, but it does leave a trail of water. So if you then stop the bearing and it's standing still, that's when you can get corrosion, which is called standstill corrosion. So in short, the WAM can be used to evaluate the lubrication performance of lubricants that are contaminated. Next, we are going to see a similar rig, which is also a ball and disc machine, that is used to look at the tribological performance in terms of friction and surface interaction from additives, and that will be shown by my colleague there, Nicola.
Hello everybody, my name is Nicola, and this here is the MTM, which is a mini traction machine. It's a small and simple tribometer. Enclosed in this small pot we have these specimens, so it's a rotating ball on a rotating disc. And as my colleague Ralph just explained, in some cases we don't actually see a direct effect of contaminants on the formation of the lubricating film. And in this kind of scenario, we should not expect to see any effect on friction either, which is what we actually measure with the MTM. However, this doesn't mean that the overall functionality and performance of the lubricant will be unaffected, because actually the functionality of the additives could be affected by the presence of some contaminants. Additives are able to chemically and mechanically interact with the surfaces of the bodies into contact to form a so-called tribofilm. So what we can do with the MTM is to employ the same interferometry technique that's been shown on the WAM, but this time in a static manner to monitor the evolution of these tribolayer. This is typically how it looks like, so we can try to understand to what extent it was disrupted by the presence of water, for example. And this could have an effect on the performance of the lubricant, particularly in the conditions where metal-to-metal contact is likely to occur. The wear performance could be affected, for example, and this is something that we can try to understand by performing a wear analysis on the specimens of the MTM after a test. However, if we want to extend this type of analysis to include a wider spectrum of possible damage mechanisms, then we have a different kind of rig that's been designed specifically to study that. And here it is, together with my colleague Thomas, who's going to explain about this. Thank you very much.
Hello, thank you for the introduction. This machine is called the microfitting rig. It gives us the possibility to study wear and surface-initiated fatigue, in this case more commonly known as microfitting. This is a phenomenon which occurs prior to spalling, which in the end leads to accelerated wear. Microfitting can be caused or accelerated by multiple things, for example, poor lubrication or contamination, for example, by water. If you follow me, I will show you an example. On the picture here, which I hope you can see clearly, we have three examples, left to right. Most left picture is a well-ly lubricated contact. The second one, you have a little bit of water contamination, and the third one has the surface has been attacked by standstill corrosion. So, of course, you can judge yourself. It goes from good to bad. We don't want this to occur in our bearings, of course. So that's on this machine you just saw. That's why we created the possibility to test lubricants, also greases, coatings and materials on their their ability to protect the surface against this phenomenon. Now I would like to show you another machine as well, which we have here. It's the following. It's called the wetting wear rig. This machine gives us the possibility to mimic or create vibrations which also occur in the field. And then this creates fretting wear. This picture, you can see an example. Well, this can occur, for example, during transportation of cars and trains or whatever. Well, if a contact is well lubricated, or we have a good lubricant, you can protect the surface against it. Yet again, if water contamination in this case enters this contact as well, it can stop the lubricant from preventing this from happening. And that is something we can research here as well. That's all I had to share.
So, thank you, Thomas. So, as we have seen, we have different rigs or different thermometers that are used to study the influence of contamination on our bearing performance in a single contact. Also, we use the same rigs to study the influence of proposed solutions against contamination, such as, for example, coatings or materials. But as a prevention and to increase the performance of our bearings, we need to keep these contaminants out. And for this, we need to have good sealing solutions. These solutions are usually developed at our SEAL Research and Development facility that will be introduced to you by my colleague Bas.
Welcome to the SEAL R&D lab. My name is Bas van der Vost, and I will give you a small through our lab. In this lab, we support our SEAL development centers around the world and our SEAL testing locations around the world with models to predict SEAL performance and behavior, and with experimental work on SEALs. Our lab basically consists of two labs. One is on SEAL material testing, and the other one is on SEAL testing. And today I would like to give you a small tour through our SEAL testing lab. We go to the first lab. In this lab you see a battery of test rigs, which is currently used to test SEAL live performance. At this moment it's used to test seals that are used in car wheel bearing units. And the performance we are testing is how well these seals are able to exclude contamination from the environment. So on one side we supply the seal with mud, and on the other side we are looking how much contamination is ingressing into the through the seal, basically into the application or into the bearing. Here we are interested, of course, in which parameters, operating parameters, are involved in the sealing performance. So dynamic run out of the shaft, shaft to bore misalignment, speed, temperature, all these factors play, of course, a role. And of course, which seal designs are best to exclude contamination from the environment. This setup, as shown here, is for exclusion of contamination, but can also be used to look into to oil seals. And there we normally test how well these seals are capable of keeping the lubricant in the application. Similarly, we are interested in the same parameters, lip design and the operating parameters. In order to perform well, these seals have to really tightly close the gap between the outer ring and the inner ring in a bearing, or between the housing and the shaft in other applications. And inevitably, this will create friction. And of course, we want to design seals which are capable of performing well, so excluding the contamination and keeping the lubricant in, but at the lowest possible friction. And for that, I would like to take you to the other lab. We go in here. In this lab, you see a row of, in this case, 3 test rigs where we can measure seal friction. Currently, they're used to also test the wheel, the seals used in the car wheel bearing units, as we were testing in the other lab as well. But here we're testing them on their friction properties. Again, with the aim to look which properties, what the friction is, and how it's influenced by the seal design and the operating conditions. In addition, these friction test rigs are used to validate our models. Our models are capable of predicting friction, as well as predicting how well the seal is able to follow the shaft or the bearing inner ring. And for that we use these test rigs to validate the models in these numerical calculations. Once we get a bit outside of normal operating condition, we go a bit into the extreme. We have to do testing, more and more testing. And for that we have an example over here. With these 2 test rigs, we can test up to speeds of 25,000 and 50,000 RPM. And these test rigs have been specially designed to test seals needed for the electrical vehicle market. And there you find these very high speeds. And in this case, the challenge is really to have well-performing seals which are capable to maintain their function at the lowest friction possible. Because if the friction is too high, you generate too much heat, due to which the seal starts to age. You accelerate aging, you accelerate the wear of the seal, but in addition, you also accelerate the aging of other components such as the lubricant. And with that, I would like to give the word to Maxence, who will tell you more about lubricant and lubricant aging. Thank you.
Hello everyone, and welcome in the lubricant analysis chapter. Lubricant and bearing analysis is performed at various sites within SKF to support local business. Here in Houten, the Netherlands, we support those centers and additionally experimental and modeling R&D activities. Welcome in the chemical laboratory. What is the goal? What is the value of the lubricant analysis? First, we can compare lubricants from different suppliers to determine the chemical components. Also, lubricant analysis is a part of the SKF services. We can determine the best lubrication interval, the best lubricant grease formulation for an application. Also, we can know the contamination and by this way determine the performance of the seal. Here in this laboratory, we have some machines to make the analysis of the lubricant. And first, we will start with the SKF test grease kit. This kit is a very simple and quick test to determine the principal characteristic of the grease. For example, the oil bleeding and the consistency. This test gives a quick status on the grease performance. Is the grease performing according to acceptation or degrading? An operator, for example, at the customer bearing application, just has to take a very little sample of grease and follows the guidelines to determine these characteristics. Thanks to that, it can directly take a decision to improve the lubrication of the system if needed, because the operator does not need to send the sample to a laboratory and waits days and weeks for the result, because here the result is almost direct. Now let's move on the card fisher. The card fisher is an analysis station to determine the amount of water inside the lubricant. This machine measures in ppms the water concentration. For example, an operator in a wind turbine will take a sample of lubricant and send it to our laboratory. With this sample, we can see if the water has an impact on the performance of the lubricant. If so, can we protect the lubricant from being contaminated? Do we need to change the lubricant interval? Or is there a better lubricant on the market with a higher water resistance? Now let's move on the synthesis of the additives, and I will let my colleague Frank Fidelas talk about that.
Thank you, Max.
Welcome.
Hello, everybody. Lubricant analysis is run to determine the status of a lubricant. So is it healthy? Is it degrading? Is it alarming? If we now go a bit deeper, then you would like to know the grease formulation. So what's inside the grease? Can we crack the grease formulation? So here, for example, particular ingredients, base oil ingredients, or additives. But what is it now specifically? How do they all interact with each other and provide proper lubrication? So what you find here is a synthesis of a chemistry, for example, an additive or a soap ingredient. And you can play and improve the chemistry, but you can play also with the temperature profile, cooling, and the mixing, all with the target to improve, for example, a certain lubricating mechanism. Think about low carrying capacity, friction, corrosion, and those type of mechanisms. Once you have such an additive, then you still need to integrate it in the rest of the grease composition. It needs to be compatible with the oil or the soap, and sometimes you need to worry about, okay, how does it then behave as a whole? So you might gain something on false benelling, but you can lose something on corrosion. And this type of studies we can do with our grease capital facility. It's a bit further, so I hope you can walk with me to the next position. Yes, I hope it's going fine. You follow me? Almost arrived. So what you find here in a second is a small grease kettle, and it's basically a small volume, so you are in a good position to control all the process parameters, and you get in the end a good reproducibility. You find here a heating installation where you can heat the soap ingredients inside the base oil to create the soap, to form the gelling process, and then you cool down, you add the oil, and a bit later you add also the additives. And in the last step you can do the proper milling, and you find here a 3-roller mill, quite intensive milling. So you understand a bit our facilities. You have over there a synthesis, you have here the grease making, and you can play with compositions, and also with all process parameters. All this is affecting lubrication. This we use for our solution development, but also for our modeling, like live modeling. Here you can also study, just for example, for high-speed bearing operations, which you find in EV application. Also the grease structure, the grease viscosity, crystallinity. This we can study here properly, and for that we have another device. This is a rheometer, also well known in this industry. I don't have that much time, but I hope it's possible to peek on this. If you can't see it, then I hope you believe me, it's there. So yes, rheology. Rheology is basically studying plastic flow and electric flow of soft substances, like a grease. So some greases, they respond very differently to the applied shear stress than others. So with this, you can improve what we just said for high speed, the friction behavior. So as you can see here, we have the synthesis, the grease facility, grease making facility. You play with compositions, but also with specific lubricating mechanism. So rheology and high speed is just an example. If we move a bit further, yes, then we'll move to the next position. This is the FTIR. You will see in a second. Please follow me. So the FTIR stands for Fourier transform infrared. What we do here is taking a sample, a re-sample from the test bearing or from the application, and place it in this apparatus. So this re-sample is then exposed to a beam of light at different frequencies. This apparatus then will generate a spectrum. So with a wide range of wavelengths, it will show you different absorption intensity peaks. Some of these peaks are correlating to the pigment ingredients, other peaks correlating to oil or to the additives. So it gives you an insight about what's inside the grease, and you can identify the type of grease. Yes, each grease has a different spectrum, as you can find here as an example. But even though the greases are quite similar in composition, you still can spot some small changes in all these absorption peaks. You can also use it in a slightly different way, is that if you take a sample, representative sample from the test bearing, from the bearing application, and you make a spectrum, and you overlay it with a fresh sample, so used versus fresh, then you find still, again, small difference in these peaks. And some of these peaks, these absorption dependency peaks, are then reflecting changes in the oxidation or degradation, or maybe there's some water ingress, or let's say some combination with another lubricant. So I hope today, in a very short way, that we could present you something on our capabilities on lubricant analysis, also on grease formulation. So the next part will be addressed by my colleague, Richard Schaken. He will discuss with you other topics.
So welcome to the polymer lab. And in this lab we have, of course, the standard technologies for analyzing polymers like DSC and TGA. But as a bearing company, we're particularly interested in the mechanical properties of the polymer. So as you can imagine, our bearings are used at a wide range of temperatures, from very low, -40 or even lower, to high temperatures of 200 degrees centigrade or higher. Also, our bearings operate at a wide variety of speeds, and so we need to characterize the polymers for a lot of conditions, because polymers are viscoelastic and viscoplastic materials. So the most instrumental machine for that is our DMA. And this DMTA, it allows us to characterize a polymer or a sealing material at different temperatures and frequencies and create a master curve that will allow us to assess the material's performance over a wide range of temperature and frequencies. So for sealing materials, we can take these data directly and use that in our simulations of sealability and followability of the seal. When it comes to polymers, they're often reinforced, and then we need to run a simulation to calculate how the fibers are oriented in the sample and calculate what the final properties will be. Now, of course, we don't blindly trust on our simulations, so we have to validate, and for that we use this tensile machine. Sweep machine we can also use the compression. We've got a climate chamber with it, so we can assess the performance of the material across a wide range of temperatures and at different loading rates, so we can verify our models, our parameters that we assessed with the DMTA. This is especially relevant when we go from existing technologies, existing materials, to new materials that are maybe needed to address new market needs. And this is the case for polymers, and it's also the case for other materials, like, for example, for the rolling elements. And for the rolling elements, for example, you can think of moving from steel towards ceramics. And for the ceramics, my colleague Anand will explain to you further.
Good afternoon and welcome to the ceramics lab. My name is Anand Houten, and I will be giving a brief tour of our facilities. Please take a walk with me. Hybrid bearings with ceramic rolling elements have several advantages over the standard steel to steel bearings. They are electrically insulating, they have a longer grease life, and ceramic rolling elements typically weigh 60% less than the steel rolling elements, and also they are less prone to seizure. All these characteristics are highly beneficial for wind turbine generators and as well as for other applications. However, hybrid bearings are very expensive. And in SKF, we are trying to work on fit for purpose, less engineered materials. This requires a thorough understanding of our ceramic materials as well as their behavior in rolling contact. Ceramic materials are defect sensitive due to their lower toughness. Hence, the inspection of these materials is very important and crucial to ensure quality as well as the reliability. At SKF, we have level 4 sensitivity fluorescent penetrant inspection suitable for aerospace industries. This kind of inspection requires a dark room, which I will show you in a moment. Let's go inside and see what a dark room looks like and how we do fluorescent penetrant inspection. In the fluorescent penetrant inspection, we immerse our rolling element in a penetrant liquid. After cleaning, we expose them to the UV light under the microscope like this one. The penetrant makes the defects which are usually not visible to naked eye visible. For example, tight cracks and nanopores. For example, we have here a crack, a tight crack or C crack, which is generally not visible in the white light or other reflected light microscopes. Now we can see them. Apart from doing the inspection, fluorescent penetrant inspection, we also do microstructure assessment and macrostructure assessment using white light and reflected light microscopes. In addition, we also evaluate the mechanical properties of ceramics. There are several methods, but here I will only discuss the strength method. Generally, they use a small ceramic bar to get the strength of the materials. However, in SKF, we have developed a unique test called notch ball test, wherein we do notch directly on the ceramic rolling element and we test them in compression to get the strength of this material. SKF has driven the ISO for this kind of notch ball test. It's actually one of the first industries to use it. After knowing the macrostructure and mechanical properties of the material, it's also important to understand the rolling contact performance of ceramics. There are several test methods by which we can do this, but here I will show you the one which is called thrust rolling contact setup. In this setup, we have two flat steel rings and with a rolling element, steel balls in between them. We can replace either the bottom steel ring like this one with a ceramic ring, or we can even replace the steel balls in this one with the ceramic balls to do the rolling contact test. After the rolling contact test, it's all important to do the post investigation to understand the surface as well as the subsurface. For surface, there are several surface analysis techniques which my colleague Arnaud Roulon will explain further. Thank you.
Yes, thanks, Alan. Hello again. I hope you're enjoying this tour as much as I am. Yes, what we also do on a daily basis to fight against friction wear is to have a much closer look at the surfaces that come in contact in a bearing, typically the surfaces of rings and of rolling elements. And what you see across the corridor is our colleague Iliana working on the XPS, X-ray photoelectron spectroscopy, which is a very advanced surface analysis technique, which gives us the molecular stoichiometry on the raceways. But we actually start from a much simpler perspective. We start from simple light optical microscopy. We have a look at the surfaces of bearings coming back from the application, and we compare it to that of the components that we test in our tribological test that are designed to mimic what is going on in the application. So we make sure that those test methods, accelerated test methods, are actually mimicking what they're supposed to mimic. And Ralph is one of our most experienced surface explorators, so he will explain how we take surface samples.
Hello. Yes, on the contour that we have here, we can measure the surface topography of our bearings in 3D using white light interferometry. When the bearings are large and they cannot be sectioned, or when they are still in operation, we cannot put them here on the stage. So then we can use a rubber compound like we have here, that we can, with this we can make a replica of the surface, and then we can measure the surface topography of the replica on the contour as if you are looking at the real bearing. So we can see, for example, here what the bearing surface looks like. This bearing is actually running in a test rig at SKFstronger. So you can follow its evolution of the surface topography during a test. Another application where we can use this is in wheel bearing units of railway trains. They are regularly, in certain intervals, they are refurbished, and before they are remounted on the train, we can take a replica, measure that here, and then we can follow the evolution of the surface topography and make a better prediction of the surface line. Next to that, we can measure the components that we are testing on our tribometers to assess the surface damage and the wear that is achieved during the test. But normally we start with a basic light optical microscopy to analyze bearing components, and that will be shown by my colleague here, Diana.
Thank you, Ralph. Yes, after the NPR test that we use to screen different lubricants and cell variants, we can look at the rollers under the light optical microscope. With the light optical microscope, we look at different features such as microfits, microcracks, decoloration, or even indication of tribopent. This is very important to identify different areas of interest, but later on can be investigated at higher magnification. We can also search some components, and this way we can distinguish between surface and subsurface failures. We can also rate the severity of the damage in the test, and later on correlate with the application. Now my colleague Arnaud will continue showing our facilities.
Thanks, Diana. Thanks, Ralph. Yes, sometimes we need to go for higher magnifications. For example, when you look at electrical vehicle bearings, sometimes they have this grayish appearance, so-called gray frosting. And for this, we need high magnification. So we use the scanning electron microscopy, SEM. This enables us to visualize feature below the micron level, and this enables us to understand the fundamentals behind friction and wear. We also use the SEM in combination with EDX to have the elemental composition of the tribal layer that forms on the raceways. And this gives us an indication of how the lubricant additives are interacting with the surface and enables us to take the screening of lubricants formulations to the next level. Boris is our SEM expert, and he will explain what we also use the SEM for. Boris, please.
Thanks, Arnaud. Good afternoon. My name is Boris Minov, and let me tell you a few words about our scanning electron microscope. As mentioned, this instrument is very often used for the surface analysis. Sometimes we get the question, which steel should be selected to show the best surface performance? To give this answer, we have to always establish the link between three different properties: surface, so topographical, microstructure, and mechanical properties. To get more information about the microstructure, we are also using this microscope at very high magnifications. By using secondary electron, backscattered, or EDX, we can give information about topography, morphology, or chemical composition of our steel, and also the phases which are present in these materials. It is sometimes also important to quantify locally, of course, on very small scale, because this is high magnification investigation, about the different phases which are present in the material. And for this, we are using EBSD detector, as image shown here. However, beside the microstructure, as I mentioned, we have also to give the answers on mechanical properties. One of the parameters which plays a very important role in the bearing performance is the residual stress. And for determination of the distribution of the stress, residual stress, on surface or bearings or on subsurface, we are using X-ray diffraction technique, or shortly XRD. This technique, beside the residual stress, helps us also to quantify different phases which are present in our materials, not only steels, also other metals and ceramics. Now, for example, in wind application, stability of the bearings during operation is dependent of the amount of, one of the parameters is, of course, is the amount of the retained austenite. Sometimes it is also not only retained austenite and ferrite to quantify, but also other phases, like, for example, in the machine tool applications. We are using this technique not only for investigations on bearings, but also sometimes on other component test specimens, and also on experimental test specimen like dilatometer. Now we are going there, where I will give you a small speech about that. Dilatometer, it is the instrument which helps us to decide which heat treatment cycle should be proposed to industry for certain steels for some applications. Now we can see here the dilatometer. In this instrument, we are determining the phase transitions which occur in the steel during cooling and heating in our controlled atmosphere. Once we confirm the final recipe, before final proposal, of course, and we are doing some experimental investigation after dilatometry work on the equipment which was shown before, we are doing the heat treatment of our prototypes, and this is done in our heat treatment lab. We are teleporting now there, where my colleagues René and Rose will give you more information about that. Thank you.
Hello everyone, welcome to our heat treatment lab. My name is Rose Yan. This is my colleague René Clarissa. Both of us are working in the bearing steel and steel processing area. Here we can perform different kinds of heat treatment cycles, including annealing, hardening, and tempering, in order to get the desired through-hardened microstructure, either in martensite or in bainite. Now you will see René in action. After the production of the sample, we will perform component testing using the facilities that you have already seen. And then we will perform post-test analysis using the microscopy techniques that my colleague Boris has just showed you. Based on those results, we will be able to select the candidates with the best performance to give recommendations to our product development and later on the new market offer. And of course, the steel and heat treatment design is not only used to produce component samples, but also to produce prototypes. Then we will perform the test in the bearing level. In the next session, my colleague Louis will show you how we perform those tests.
Good, thank you, Rose. So we've now seen several different bearing components. We've seen the steels, we've seen the heat treatment of these steels, ceramics, we've seen the gauges and the different steel components, but we did not see the full bearing arrangement yet. And that's what we're going to have a look at now. So the full bearing package, which will give us eventually the bearing performance. And of course, these also need to be tested. And that's what we're going to have a look at now. We're going to have a look at the different test rigs, or a small selection of them, which we have here in Houten, in the building in the Netherlands. So please follow me. We're going to do this, which will show you the first of these bearing test rigs. Please enter here. Aziz, I give the word to you.
Thanks, Stuart. Good afternoon, everyone. I would like to show you the test setup in SKF to understand the bearing's electrical behavior in an e-motor of an electrical vehicle, which includes battery electrical vehicle and hybrid electrical vehicle. We use this test setup to evaluate the bearing's capacities at varying operating conditions, such as load and speed. This helps us to understand different design parameters of the bearing and their effect on resulting capacities. In addition to that, we have been able to develop methods and equipment to reproduce common mode voltage phenomenon observed in variable frequency drive driven motors. This further enables us to understand and reproduce gray frosting and fluting in standard steel bearings. With this understanding, SKF can help the customers with in-house developed solutions, both conductive and insulating, to prevent or mitigate the electrical current damage on a system level. This prevents any damage of the components in e-powertrain. Thank you. Lieve, now it's your turn.
Thank you, Aziz. So that was a very application-specific problem. Here we are having a rig where we are investigating more a general bearing challenge, and that's lubrication. With this rig, we have a look at the grease lubrication. It's a small size grease life test, which we also use in our grease life testing and our modeling. But this one we use for a different purpose, and that's the research purpose. As Frank was already mentioning in the past, we can have a look at grease degradation and grease aging. And that we do, for example, on small size HVB bearings for the EV application. The EV application has very high speeds and very high temperatures. Then we have a look at how the grease degrades in time under the different temperature and different load conditions. We can have a look at different applications as well with this rig. For example, with cylindrical roller bearings, which we typically have in railways, of course a bit bigger than these ones. But with this we can simulate what happens to the temperature evaluation when we have a look at different load and different speed conditions. So how does the temperature evolve with the different conditions? That we can simulate with this small rig, and we can then use later on in the selection of the right properties, of the right greases, of the right additives, to make a good choice for later further testing, which you'll see later on as well. So that we can do with this small rig, a very versatile rig, where we can test a lot of different bearings in a quick and easy manner. Now we have to Marco, to our other lab, which will show you something about Houten. Marco, go ahead.
Hello, welcome in our lab. I'm going to show you our Houten rig. So this is our Houten rig, and here we can put in this box an electromotor and cool it down to minus 30 degrees. So why do we want to do that? That's because especially at low temperatures you get the hooting noise. Now imagine you have bought a brand new car with an electromotor, and in the morning you want to drive away and start it up. And suppose that this motor was not designed well, then you can have the hooting noise. I will show you how it sounds like. So sorry for that, it's really annoying. And it can be very loud, it can be up to 120 decibel, which means your whole neighborhood will wake up. Now the hooting noise is caused by the influence of the lubricant, the grease, and the motor dynamics. And the good news is that in SKF we have studied this intensively, and we have learned a lot, and we have developed several solutions how to prevent this. And yeah, that means that we can give advice to our customers, and of course for that reason they like to work with us. I will show you more bearing test rigs. We are going to our colleague Mura. Thank you.
Thanks, Marco. My name is Murat Chanawi. I'm senior researcher at SKF, and today I would like to talk to you about bearing imaging test rig. This rig consists of a bearing which can be run at various speeds and load, and is coupled with a high-performance optic and an imaging module for grease flow visualization and investigation. Essentially, what this test rig allows us to do is to better understand how the grease flow inside the bearing, so that we can optimize the way to reach where it matters the most, which is the contact. This type of investigation are even more so important to improve the reliability and the performance of our bearing in high demanding applications such as electrical vehicles, where the speed can be extremely high and the temperature as well, or railway, where the maintenance interval can be relatively long. So I would like to show you here on this screen a clip of a grease flow between two rollers. As you can see, the rollers are being lubricated with grease, which gets then carried on from one roller to another. Of course, there's much more that I can see here, but unfortunately, this is all the time we have here for today. So I would like to thank you for your attention. I will now hand you over to my colleague, Li Wei.
Thank you, Murad. So this live event was all about friction and wear and how to prevent it and what to do about it. We did not have a look yet at how friction looks like inside a real bearing application. And that we're going to have a look at next. It's one of our frictional test rigs. With that rig, we can test under different application conditions, similar loads, similar speeds, and also similar temperatures, how the friction evolves. And that we can do with different bearing types, with different bearing configurations, so single bearing or multiple bearing configurations, and to have a look at how the friction evolves under these conditions. That input, the frictional data coming from these rigs, we use to select different greases, select different additives again, and use that input as well into our frictional models like SKF Simpro Expert. With that information which you obtain in these rigs, we can make a good selection of greases for our customers. So you've seen now several rigs inside SKF Houten. As you can see, we have several more, which we cannot show you at the moment. That we'll keep for another SKF live event. So now I would like to give the word back to Sadvik.
Welcome back. We hope you enjoyed the tour. We are almost reaching into the end of the session now. And before we reach really into the question and answer, we wanted to share a few more words. What we have witnessed in last 50 minutes is the new facilities of R&D in SKF at Houten, Netherlands. We hope that you are able to visualize how we utilize these facilities to develop application-driven R&D into the next level. At the end part of the tour, you would have witnessed we are talking about many bearing test rigs. Bear in mind, SKF also has many bearing test centers across the globe. So these test centers will be utilized to mainly bearing-like testing, grease-like testing, component-based testing, and also certain functional testing which are specific to application. And these tests will help us to make the reliable rotation and also to take the technology and solutions into the next level. To name few of our test centers, first of all, SKF hosts one of the powerful test center for wing main shaft bearing in SKF Frankfurt, Germany. SKF also has railway test centers in Asia and Europe. SKF hosts one of the finest capabilities in high-speed testing, including electric vehicle solutions. Recently, bearing-like test has moved to Italy and India. The data obtained from these tests were utilized in developing the new SKF bearing-like model called as GBL. In general, data obtained in Houten and also across many test centers throughout the globe will not be utilized only for the purpose of application-driven R&D. It is also utilized to develop the reliable models for our application engineers and also for our customers. Now we'd like to add a few more remarks before we really move into the question and answer.
Thanks, Sadvik. Yes, I hope you have enjoyed this tour, and I would like to thank you for your participation and for your curiosity. I would also like to thank the different contributors to this tour, and especially people that have been working in the background, like the camera operators sitting behind, the producer, the moderator, etc.